Okay, we're going to go ahead and get started now. And today we're going to start the chapter on chemistry. I think we finished up chapter 1 on introduction on Monday, and so today we're going to go into chemistry. And hopefully I'll try to keep it as interesting as I can as we go along here, because a lot of the chemistry that we're looking at is directly related to what's going on in our bodies, all the chemical reactions that occur, because chemical reactions drive our action, drive what we do. So that's why we have to understand the chemistry we're looking at. Let me get into the first. Everybody should see the slide that says chemical level of organization. So again, the reason why we focus on chemistry is because our body chemistry can tell us a lot of things about what our body's doing. Something as simple as breathing fast after exercise. Breathing fast after exercise is driven by a rise in carbon dioxide, the gas that we breathe out of our lungs. When we exercise, we burn glucose. We burn glucose for energy. A byproduct of burning that glucose in our bodies is a release of carbon dioxide. That carbon dioxide is converted to carbonic acid when we in our blood. So we have this acid in our blood, making our blood more acidic. Our brain picks up on that. And this chemical reaction of combining carbon dioxide and the water in our blood into carbonic acid, our brain says, wait a minute, we don't like that. So it tells our lungs to breathe faster. And the whole reason we breathe faster during exercise is not to get more oxygen, but to blow off the carbon dioxide. That's a chemical reaction that drives that. So understanding how chemistry works in our bodies is actually a pretty important thing. So to begin with, to look at chemistry, we have to understand what matter is. Because we're made of matter. Matter is anything that has mass and takes up space. We can see matter, we can feel matter, we can touch it, we can smell it. If we're smelling chemicals, odors in the air, those molecules that are causing the odor are still part of matter. They are real structures. Now, matter has mass. It doesn't always have to have weight. And a 160-pound individual on the Earth still has a mass of 160 pounds, but has no weight when they're in the space station, because weight is caused by the effect of gravity on our body mass. So everybody has mass, regardless of their location, whether they're on the moon or on the Earth or in the space station or in orbit, they're in the water, we still have the same mass. If you weigh 160 pounds on the Earth, if your mass is 160 pounds on the Earth, your mass on the moon is still 160 pounds. You may not have a lot of weight because of the limited gravity on the moon or zero gravity in orbit. Anyway, enough of that. So how do we define what matter is? Well, matter can be in 3 distinct different states. It can be a solid, like ice or a brick. Or a Snickers bar. It can be a solid. It has a definite shape and a definite volume. If you have an ice cube, you expect your ice cube to have a definite shape to it. You expect a candy bar to have a definite shape. A piece of bread has a definite and defined shape. It has a certain weight. It has a certain volume, it has a certain shape, it has a certain mass. And that's what a solid is. A solid has, we are solids because we all have defined shapes and defined volumes. Your computer, your phone, your chair are all defined shapes and have defined volumes. A solid doesn't usually change its shape unless it's destroyed. Now, liquids are the second category of matter. Liquids have a defined volume, but their shape changes. If you have a gallon of milk, that's a volume, a gallon of milk in a container. If you empty the container, the milk that was contained in the container, assuming the shape of the container, now spreads out wherever you've poured it. Maybe you pour it into a glass and it assumes the shape of the glass. Maybe you pour it into a bowl of cereal and it assumes the shape of the bowl. Or you just knock it on the floor and it covers the floor and assumes the shape of the floor. So a liquid can change its shape, but it's still going to be the same volume. A gallon of milk on the floor is the same volume as a gallon of milk in the container. And a gas sort of breaks the rules here because gases have changeable shapes and volumes. For example, if in the classroom here, where I'm lecturing from, if we took all the air out of this classroom and sucked it into a compressor, we could compress that air and put it into a very small tank. Classroom air, room 217 classroom air, January 26th, whatever today is. And that would, it would fill a small tank, maybe the size of a fire extinguisher, for example. That would be the air. It was compressed. The volume changed. It was compressed into a small volume by pushing all the molecules of the air together. It went from filling up a classroom to filling a small container. Its shape changes. It goes from stretched out to a very small shape. We can even compress it further and the shape will become even smaller. The volume will become even smaller. We can even cause it to become a solid. If you compress air enough and push the molecules together enough, it will become a solid. It will become liquefied and then freeze. So you can change it from a solid to a liquid to a gas, or a gas to a liquid to a solid. We see that happen all the time with ice. Ice is a solid, but then it starts to melt and it turns into a liquid, and then it evaporates and it turns into a gas. Okay, now energy. Now we talked about what matter is. Matter is a solid, a liquid, or a gas. A solid has a defined shape and defined volume. A liquid has a defined volume, but a variable shape, and gases don't have a defined anything. The other half of chemistry is energy. Energy is the ability to do work or move something. We use energy all the time. We manipulate our environment. We think. Thinking requires the use of nerve impulses, which are electrical energy. Now, energy has no mass, takes up no space, can't be destroyed, can't be made. The amount of energy in the universe is fixed. We can use energy and we can convert it from one form to another. We never destroy energy. We don't make new energy. When we're generating electricity, for example, we're simply converting stored energy in water power or in gas or coal or solar. We're converting that energy into electrical energy. We're not making new energy. We're just converting it from one form to another. This example here, this is Newton's cradle. And you've probably all seen these before. But what's happening here is the ball bearing on the left is hitting the three ball bearings in the middle and causing the ball bearing on the right to fly out. What we're doing is we are transferring energy from one ball bearing to another. And we go through the three in the middle to do that. So that the energy we're doing work. Doesn't look like we're doing work, but we're doing work. We're manipulating the environment so that we hit the ball bearings and they fly out the other end, and then it comes back and knocks the other one back and forth and back and forth. And it's just an example of the transfer of energy. Yeah. Energy does come in two key forms. It's either kinetic or it's potential. Kinetic energy is the energy in motion, doing things, movement, manipulating our environment. Kinetic energy, lighting a candle, lighting a match, throwing a ball, driving your car. That's kinetic energy. Potential energy is, one of the definitions is energy at rest. I like stored energy better. The energy that you get when you eat a Snickers bar or an apple. We measure that in calories. An apple has about 60 calories in it. A Snickers bar has 160 calories or thereabouts. A slice of bread's about 40 calories, things like this. When we say calories, we represent the potential energy stored in the food item. Calories the use of calories is a way to measure the potential energy stored in food. We measure energy on our phones. For example, you plug your phone in at night and you charge it, and the next day you take a look, it says 100% charged, or you discovered that the charger wasn't plugged into the wall and you're still running at 18% or something like that. So that's potential energy. You charge, you measure that on the scale on your phone. It tells you what percent of the battery is charged. The battery is taking electrical energy and storing it so that you can use it later. Potential energy, stored energy to be used. You put gas in your tank or diesel in your tank. That represents stored energy. And you use that to power your car. And you use, how many miles per gallon you get depends, but you're using the stored chemical energy, the potential energy in the fuel tank to power your vehicle. You don't use it all at once, but you do use it. And we go back and forth between potential energy and kinetic energy all the time. We're walking around, we're using kinetic energy to power our muscles. We're doing things, and we're drawing on the energy reserves stored in our body. That's potential energy. You ate an apple, or had a bowl of cereal, or had that Snickers bar that I keep talking about. The calories stored in food represent the potential energy that our bodies can draw on to use. We reload our bodies every day with food to get more calories so we can power our activities. You don't use, if you eat an apple, you don't use all 60 calories at once, but they're available to you. You don't use all 160 calories in a Snickers bar, they're available to you, or 200 calories in a bottle of Coke, they're available to you. We can use them. We use that all represents potential energy. And when we convert the potential energy to kinetic energy, we get some sort of action, some sort of motion, some sort of manipulation of our environment. Now here we see an example of the difference between kinetic energy and potential energy. So we have this individual holding a bow and arrow about 3 feet from the target, so it makes it really easy for them to hit the target. Right now, the bowstring represents potential energy. Right now, the potential energy of that bowstring is pretty low. However, if we add kinetic energy to it, we can store energy in the bowstring. Because if you have a bow and you draw the bow back, so now the bow is under tension. The string is under tension. The bow is ready to go. That's potential energy. You're not doing anything. You've pulled the string back. You've applied energy to that string, and it's stored up there. And when you let it go, you release that potential energy, and it's transferred to the arrow, and the arrow moves through the air, and it hits the target. And the arrow has mechanical energy because it's moving through the air. It's been the potential energy stored in the bow, in the string, transferred to the arrow. The arrow moves through the air, it hits the target, it transfers its mechanical energy to the target, punches a hole in the target, transfers some heat to the target, and it's done. And we can do it again. So let's see what happens here. Okay. So energy is the capacity to perform work, and we store potential energy when we do something that is kinetic energy. As I said, we don't create energy, we don't destroy energy, we can simply convert it from one form to another. So our bow and arrow has low potential energy. We apply kinetic energy to the bowstring and to the bow, and we pull the bow back, pull the string back, and now there is lots of potential energy in the bow and in the string, and we release it. That's all transferred to the arrow, and it hits the target, punches a hole in the target. Mechanical energy in the arrow is transferred to the target along with a lot of heat, because the arrow heats up as it moves through the air. So there's a certain amount of heat transfer at the point that the arrow is going to impact the target. You can actually measure that fairly well. So there's always friction. There's always friction. And as the arrow moves through the air, it's going to hit those air molecules around it, and that's going to create friction. It's actually going to slow the arrow down a little bit. Not that we can notice, but it will slow it down a little bit because the friction of the air molecule on the arrow causes it to warm up. Now, the energy that we get to pull the string back comes from the food that we eat. The apple, the banana, the cheeseburger, the Snickers bar, the Coke, the cereal, whatever we eat. The stored energy in the food is transferred to our body. You know, the chemical energy in the food is transferred as chemical energy in our bodies. And we use that to power our muscles to do things like pulling the bowstring back and to release the bowstring. And so we're using, as we see here, we're using lots of energy to pull the string back. We are giving off a certain amount of body heat, because every time we transfer from one form to another, a fair amount of that energy is lost for us to use. It's lost as heat. It doesn't get destroyed. It just doesn't stay available to us. So we always lose a certain amount of energy as heat every time we transfer it. Then we let go of the arrow and it flies to the target, and we've converted all the chemical energy we've used into mechanical energy. And even then there's a little loss as heat as the arrow moves through the air. So let's go on here. Now, if you've been on a roller coaster, like at Dollywood, for example, you know that you go up the first ramp and it's very, very steep. And you suddenly realize at some point that as steep as that ramp is going up, it's going to be just as steep coming down. And so when the cars go up the first ramp, they are acquiring a great deal of potential energy, because they're being lifted up, you know, however many feet in the air that is on the ramp, and you get to the top, and now all that stored energy has to get paid back, and it's paid back as kinetic energy. You notice how the blue bar goes up when you go up the first ramp, The blue bar rises as you're gaining more and more potential energy, and then you release that as kinetic energy when you go down the other side, and then you store it up again in the second ramp and the third ramp, and you every time you go down a ramp or down through the circle, around the circle, you're going to use up a lot of kinetic energy. There's still the price to pay in heat loss. There's friction of the wheels on the rails. There's friction on your body as it goes through, as the air hits it as we go along here. But that is kinetic energy versus potential energy. The same thing applies to our bodies. Food provides us with potential energy. We can convert that potential energy into kinetic energy when we move our muscles, when we pump our blood, when we breathe, when we think, because we use electrical energy to do any kind of nerve impulse. So in human anatomy, there are 4 different types of energy that we deal with. Of course, chemical energy. We store energy in our bodies as chemical energy. We store it in fat cells. Adipose tissue contains fat. Fat is a great source of energy. 1 gram of fat contains 10 calories of energy that our bodies can use. We have lots of fat cells in our muscles, for example, because it's a great way to store a lot of energy. Carbohydrates. We use carbohydrates as our primary fuel source. We convert everything to carbohydrates because a gram of carbohydrates, sugars, if you will, contain 4 calories of energy. So that's what we use as our fuel source. Everything gets converted, all fats get converted to carbohydrates, all proteins can get converted to carbohydrates. And of course, the carbohydrates we take in, the sugars and the pastas and stuff like that, are all converted to a simple sugar. That's chemical energy. We have electrical energy in our bodies. Muscle contractions and nerve impulses depend on electrical energy. Our muscle cells have a charge on them. Every muscle cell has a charge of about minus 90 millivolts. It's measurable. Every nerve cell has a charge of about minus 70 millivolts. That's also very measurable, and we can monitor the changes in the charges over time. So the ability to stimulate our muscles, to send nerve impulses from our ear and our eye to our brain, and then send other impulses out to our muscles and glands, is all electrically charged. Mechanical energy depends on movement, pumping blood, responding to a stimulus, to hearing sound. Sound depends on pressure waves moving through the air, hitting our eardrum, causing the eardrum to vibrate, sending those mechanical vibrations into our inner ear and stimulating our auditory nerve to send a nerve impulse to our brain and say, hey, guess what I just heard? Mechanical energy, moving matter, manipulating our environment, hearing sounds, pumping blood, all the chewing food, digesting our food, pushing food through our digestive tract. That's all mechanical energy at work here. And the last one is radiant energy. Well, of course, when sunlight hits our skin, it makes our skin warm up. Heat energy for that. We use ultraviolet light from sunlight to make vitamin D in our skin. Plus, we depend on the visible light spectrum, red, orange, yellow, green, blue, indigo, and violet, so that the light rays coming off of objects allow us to see things, because those light rays penetrate our eyeballs, go to the back of our eyeball to our retina, and the light energy from the light rays are converted to electrical energy so that our eyeball can detect something and send a signal to our brain, and our brain can tell us what it is. So we depend on heat energy, which is a radiant energy, light energy, which is electromagnetic, as well as ultraviolet, which is also electromagnetic. So we depend on all four of these categories of energy to survive and do things. Now, every time though, as I said this before, every time we use energy, we do something with energy, we usually convert it from one form to another. Example, turning on a light converts electrical energy coming through the wall, coming through the wiring, into radiant energy in the form of a light. You know, the light bulb comes on. So we have radiant energy now lighting up the wherever we are. You know, just turning the switch. So we convert from one form to another. We turn up the thermostat in our house if we're cold. And that causes, we turn up the thermostat, that causes the heater in your furnace to send more electricity. If it's electrical furnace, it sends more electricity through the wire, and the wire glows hotter. It increases the resistance of the wiring, and the wire gets hotter, and that heat is transferred to the house. Or you burn a little more natural gas or propane, or however you heat your house, or maybe you throw another log in the fire. That is still throwing a log in the fireplace or into a wood-fired furnace or wood stove or whatever. Chemical energy from the log is being converted to heat energy in the fire. Or you're burning natural gas in your furnace. Those are all converting different types of energy from one form to another. Electrical to light, or electrical to heat, chemical to heat. These are all conversions. The problem with any kind of conversion of energy is we always lose a certain amount of it as heat. Once we get to heat energy, the heat energy radiates away from us so quickly that we can't recover it. So we can convert from one form to another very easily, but once we convert to heat, it spreads out so quickly it's no longer useful. It's still there, it's spreading out indefinitely, but we can't use it anymore. I mean, think about a fireplace or a fire pit. You know, you're sitting in front of the fireplace, you have logs in the fire, and the fire is burning, you're sitting in front of the fire pit, and it feels, you're standing about 2 feet away from it, it feels really, really good, and your front side is feeling nice and warm, your back side's cold. Because you're facing away, your backside's facing away from the fire. Your front feels good, back doesn't. But if you're 10 feet away, you can see the fire, but you can't feel anything. Heat energy dissipates so quickly that at 10 feet from a fireplace or a fire pit, you're not going to gain any benefit from it other than, oh, it looks nice. The fire looks nice. When you get closer, you feel better. You feel warm. I mean, you come in on a cold night from the outside and there's a fire in the fireplace, or you go up near a fire pit, the first thing a lot of people do is turn around so that their backside is near the fire to get that warmed up too. Because once the heat spreads out, it spreads out pretty quickly, and we don't have a way to capture it. Our bodies give off heat all the time. In our we convert the chemical energy stored in our food to chemical energy that we can use. We only capture about 40% of that chemical energy from food to using it. So assuming we have a 100 calorie apple, we only get to use 40 calories of that energy stored in the apple to do something. The other 60 calories are lost to us as heat, because the conversion of chemical energy from food to chemical energy in our body, while they're both chemical energy, we are converting it into a different form and we lose heat. And that heat is what drives our body temperature. The fact that 60% of the energy that we take in our food is lost as body heat. It does guarantee that our body stays at 98.6 degrees Fahrenheit or 37 degrees Celsius all the time. So while the heat is lost, it does keep us at a constant temperature. Okay. So let's take a look at what matter is made of. Matter is made of elements. Elements are substances that have certain specific properties, and they can't be broken down into anything less than the element. That's a confusing statement. You can't break down an element into something simpler. You know, if you have gold or silver or carbon or oxygen, you can't take the carbon and make it something simpler than carbon. Elements can't be broken down into simpler substances. Now, water is made up of two elements, oxygen and hydrogen. You can break water down into oxygen and hydrogen. You can break it down to its two components. You know, water is H2O, two hydrogens and an oxygen, but you can't break the hydrogen down to something less than hydrogen. You can't break the oxygen down to something less than oxygen. Elements can't be broken down any further. They can't be simplified any further. Everything is made of elements. Now, in our bodies, 96% of our body is made of only 4 elements: carbon, hydrogen, oxygen, and nitrogen. The other 4% comes from 20 different elements. 9 of them make up about almost 4%, and then 11 of them make up the last 0.01%. These trace elements, you know, we know we're made of carbon, hydrogen, oxygen, and nitrogen, but we also use iron, that's an element, and calcium, that's in our bones, that's an element. We use sulfur, and we use potassium, and we use magnesium, and we use, what else? Chlorine, and whatever. The rest are escaping me, but they're all in very small amounts. Got to have iron for our red blood cells. Got to have calcium for our bones. Got to have phosphorus for our bones. Sulfur shows up in chemical bonds. Potassium is found inside of our cells. Chlorine is found in our plasma. Sodium is found outside our cells in our plasma. All these elements are found in different parts of our body, but the big 4 are carbon, hydrogen, oxygen, and nitrogen. Now, we have all the known elements displayed in what we call the periodic table. Now, if we look at the periodic table here, we see all the elements highlighted in green are found in the human body. Hydrogen, carbon, nitrogen, and oxygen, they're the big 4, plus sodium and magnesium, calcium and potassium, phosphorus, sulfur, chlorine, and then trace amounts, iron and cobalt and copper and zinc and selenium and tin and cadmium, you know, all in very small amounts. But the big ones are all highlighted there in green. And the big 4, hydrogen, oxygen, nitrogen, and carbon, make up 96% of us. Now, if you're an element, you're made of atoms, always. Elements are always made of atoms. Atoms then are made up of subatomic particles that give us their distinctive properties. Now, an atom of an element will have all the properties of an atom, of that element. An atom of an element will have the same properties as the element. An atom of gold has the same properties of gold. It will melt at the same temperature. It has the same luster as gold. It has the same strength as a block of gold. It has all the properties of that element, even down to the level of the atom. The atoms, however, are assembled, they're all assembled differently. Their subatomic particles determine what element they belong to. Now, if you are an atom, you can easily determine what your name is by looking at the periodic table. Periodic table has a little shorthand mechanism here, usually using the first letter or first 2 letters of the element to tell you its name. So if you're an atom, you have what's known as the atomic symbol above your name, above your shorthand. And that tells you, hey, I am potassium, I am oxygen, I am chrome, I am selenium, I am lead, I am silver, And on the periodic table, this atomic symbol tells us what it is. And that's not enough, though, because I said that the properties of the individual elements are determined by the subatomic particles within the atoms. What are the subatomic particles? There are only three of them, three types: protons, neutrons, and electrons. Every atom will have protons, neutrons, and electrons. Except one. Hydrogen doesn't have any neutrons. Every atom will have protons and electrons, and most of them have neutrons. Protons have a positive charge. They have a mass of 1, called their atomic mass unit. Proton has a positive charge, has a mass of 1. Neutrons have no charge, they're neutral. They also have a mass of 1. So the mass of an atom is based on the presence of protons and neutrons. The electron has a negative charge and no mass. But it is very, very important, because the negative charge on an electron, tiny little electron, will balance out the positive charge on the proton. Doesn't matter how big the proton is and how tiny the electron is, the positive charge on the proton is balanced by the negative charge on the electron. And so our atoms will always be balanced. Every proton in an atom is balanced by an electron. Now, it is the combination of protons and neutrons and electrons that give each atom its unique properties of the element. So, for example, if you are a hydrogen atom, every hydrogen atom will always have 1 proton and 1 electron. Always. Every hydrogen atom will have 1 proton and 1 electron. That is its unique property. Nothing greater and nothing less. 1 proton, 1 electron. Helium has 2 protons and 2 electrons. Always. It will always have 2 protons and 2 electrons. Helium and hydrogen are not the same. They're number 1 and number 2 in the periodic table. They are different. They are completely different. Hydrogen's explosive. Hydrogen will burn. Helium is non-explosive. Helium is what we say inert. It doesn't react with anything. Hydrogen reacts with everything and everybody. Helium doesn't. That's why we don't, helium is lighter than air. So is hydrogen. Atmospheric air is made up of oxygen and nitrogen, and the molecules in atmospheric air are fairly heavy because they're larger atoms. Hydrogen and helium are very small atoms, and they're lighter. Helium balloons float. Who hasn't had a helium balloon at some point or played with helium? There's a reason why we don't give out hydrogen balloons, at street fairs and things like that, because they explode. It'd be very exciting for a short period of time. But the makeup of the subatomic particles determines what the atom is going to be, and that's going to give it the properties of the element. So hydrogen always has 1 proton and 1 electron. Helium has 2 protons and 2 electrons. It also has 2 neutrons thrown in there, but they don't do anything about the charge because neutrons are neutral. Lithium, the number 3 element on the periodic table, has 3 protons. It has 4 neutrons, but it also has 3 electrons. lithium will always have 3 protons and 3 electrons. Just like helium will always have 2 protons and 2 electrons, and hydrogen will always have 1 proton and 1 electron. And the makeup of the subatomic particles determines the property of the element. Just the way it is. Now, how do we tell these apart? Well, there are some little factoids here. We have what's known as an atomic number and a mass number, and we have things called isotopes, and we have the atomic weight of an atom. And all that is conveniently displayed on any periodic table. First of all, the atomic number always tells you how many protons are in a nucleus of the atom. Nucleus is the middle of the atom. The protons are clustered in the middle with neutrons if they have neutrons, and electrons are going to be in orbit around the nucleus, spinning around. Protons in the nucleus, that's the atomic number. And on the periodic table, you'll have a number in red above the abbreviation. For example, carbon has a 6 above the letter C. The number 6 above the letter C on the periodic table tells you that it has 6 protons. There are 6 protons in the nucleus of a carbon atom. But that also tells you that there are 6 electrons, because protons and electrons are always balanced. If you have 6 protons, you have 6 electrons. If you have 8 protons, you have 8 electrons. If you have 22 protons, you've got 22 electrons. Always. On a balanced atom, you will always have an equal number of protons and an equal number of electrons. So that's the atomic number. That one number above the symbol tells you both protons and electrons. The mass number is usually written at the bottom underneath the symbol, is the mass of the atom, and it is the sum of all the protons and the neutrons. Hydrogen has a mass of 1 because it only has 1 proton. Remember, electrons don't have any mass, so they don't count. Protons have an atomic mass, have a mass unit of 1. Every proton has a mass of 1. So if you have 10 protons, you have the mass is 10. If you have 20 protons, the mass is 20. You simply add up all the protons and neutrons, and that gives you the mass number. If it's 24, if it's 34, if it's 12, whatever. For example, carbon has 6 protons, 6 electrons. Electrons don't count for atomic mass. It also has 6 neutrons. So the mass number for carbon is 12. So underneath the letter C in the periodic table, you're going to have a 12. 6 on top for number of protons and a number of electrons. 12 at the bottom, because there's also 6 neutrons in there. So that big red number above the symbol can tell you an awful lot. Because you know, if your mass number is 12 and your protons, if there are 6 protons, that means you have 6 neutrons. If your mass number is 12 and you have 6 protons, that means your number of neutrons you have is also 6. What if your mass number was 14 and you're dealing with carbon? Well, it still has 6 protons. But if your mass number is 14 and your protons were 6, that means that you have 8 neutrons, because 14 minus 6 is 8. So the mass number can also tell you how many neutrons you have in the nucleus. So you're given directly, you are directly given the number of protons, which also tells you the number of electrons. And the number of protons subtracted from the mass number at the bottom of underneath the symbol tells you the number of neutrons. So, and that can become important later on when we're dealing with radioactive substances. So what's an atom look like? Well, we can't see an atom. There have been some images captured of atoms, but they are, they're so infinitesimally small, and they're traveling at the speed of light, which is 186,000 miles per second. So it's pretty hard to get a picture of an atom. But in a balanced atom, the protons and the electrons are equal, and they are kept in usually the same places. We find that the protons are found in, we find that the protons are in the nucleus of the atom, and the electrons are in orbit around the atom, around the nucleus of the atom. So protons and neutrons are in the nucleus, electrons are in orbit. And there are two ways of looking at this. One's called the planetary model of an atom. The other is called the orbital model of the atom. Planetary model simply looks like a little solar system. It has the nucleus in the middle, like the sun, and the electrons are in orbit around the nucleus, like the planets go around the sun, like Mercury, Venus, and Earth and Mars and so on, or like the moon goes around the Earth, or satellites in orbit around the Earth go around the Earth. So we have the planetary model. It is the simplest version of this. It makes sense to describe it this way to us so that we can visualize where the electrons are in orbit. Now, granted, those electrons are moving at the speed of light, 186,000 miles per second. And we don't know exactly where they are because they're moving so rapidly. We can't process in our heads 186,000 miles per second. We can't process that. So the chemists will tell you that the planetary model is outdated and nobody uses it. Well, we do because it makes sense. The orbital model is probably a little more realistic, though, as far as if you want to be precise in how the electrons are moving around the atom, if you really want to be precise, then you take into consideration the fact that since they're moving so rapidly, all we would see is a fuzzy cloud around the nucleus. We wouldn't see the electrons, we wouldn't see the orbits because they're changing so rapidly. And we look like this. This is a planetary model. This is helium. Protons in the nucleus and 2 electrons in orbit around the nucleus, spinning around, balanced with 2 protons in the nucleus, 2 negative charges, 2 positive charges. We can see them in a ring, in an orbit, in a shell, in an orbital, just like the moon going around the Earth, or just like the Earth going around the sun. The reality is a little harder to wrap your head around because the electrons are moving so fast that they just look like a cloud. You see this illustration here on the right. There's the nucleus in the middle, but then we see the nucleus is made up of protons and neutrons, but the electrons move so fast, all we would see is a fuzzy cloud if we could get a picture of it. But at least we know where the electrons are. We know they're in that cloud. We can't see an individual electron. As I said, they're infinitesimally small. I'm not going to push my luck and say that word again. I've said it twice and haven't tripped over it. So they form this fuzzy cloud because they're moving so rapidly. This is a more precise view, but I like the planetary model. I know it's not accurate for what the electrons are really doing, but it lets us see what the electrons appear to be doing to us or doing for us. Okay. Typical structure, 3 atoms right here. Planetary model. Hydrogen, 1 proton, atomic number of 1. 1 proton, 1 electron, no neutrons. There's your electron in orbit around the nucleus. The nucleus is just a proton, but 1 positive charge is balanced by 1 negative charge. And it just spins around. It just spins around that nucleus all the time. The second atom here is helium. 2 protons, 2 neutrons in the nucleus. It has 2 protons. That means it has 2 electrons. And the 2 electrons are in orbit around the nucleus in that first, what we call the first shell or first orbital right here. So they're always spinning around. Here we see the third element, lithium. Lithium has 3 protons, 4 neutrons, and 3 electrons. We know it has 3 electrons because it has 3 protons. The 3 electrons are in orbit around the nucleus. But notice now we have a second orbit, or a second shell, or a second orbital. I'm going to probably use all 3 different terms interchangeably. We have 2 electrons in our first orbit, and our third electron is in a second orbit. Because it turns out this first orbital, this first shell, can only hold 2 electrons. But we've got 3, so we have to go to what we call a second shell, a second level, a little further out from the nucleus. And we can hold up to 8 electrons out here. So we put our third electron out here, and the atom is balanced and it's happy. If it could be happy, it would be very happy. Now, there is an exception to all this. There is an anomaly. It has nothing to do with protons and electrons. It has everything to do with neutrons. There are things called isotopes. An isotope is an atom that has a different mass number. And it has a different mass number than all, it has a different mass number than all the rest of the atoms in that element, like carbon. Carbon has a mass number of 12 because it has 6 protons and 6 neutrons. But what if you have more neutrons? And so that's what an isotope is. An isotope has more neutrons than the expected number of neutrons. So for example, carbon-14, very common form of carbon. Carbon-14 has 8 neutrons instead of 6. It has a mass number of 14 instead of 12 because it has 2 extra neutrons. It's an isotope. It's what we call a radioisotope because it's radioactive. It's unstable. An isotope doesn't want to be an isotope. An isotope is releasing energy because it takes extra energy to hold those 2 extra neutrons in the nucleus. See, the protons and neutrons are held together with this subatomic glue, if you will, this attraction to each other. And a normal carbon atom of carbon-12, 6 protons, 6 neutrons, is very, very stable. Most carbon that we encounter is carbon-12. But sometimes we encounter carbon-14. Carbon-14 has 8 neutrons, and it has to use more energy, more subatomic glue to hold those other 2 electrons and other 2 neutrons in place. And the atom doesn't like it. So what it will do is it will release energy. It will release energy from the nucleus so that it can eventually kick those 2 extra neutrons out. And the amount of energy it releases is measurable over time. And we call it radioactivity. Gamma rays, alpha particles, and beta particles are high energy releases from the nucleus, from the energy holding those other 2 electrons in there. The atom is unstable and it will decay, releasing energy over time until it releases enough energy that those 2 neutrons are gone, and that carbon-14 eventually decays down to carbon-12 and it's stable and happy. We do know that the amount of energy released from a radioactive isotope is a constant. We know exactly how much it's going to release over time. We measure it in what we call the half-life. The half-life is how long it takes for half the energy in the nucleus to be lost, to be released. So we have a half-life for radioactive carbon estimated to be 5,000 years. So in 5,000 years, theoretically, half of the energy in a carbon-14 atom is gone. And every 5,000 years after that, it would degrade too. Math calculated out to demonstrate this. Now, this radioactivity is a known quantity. And this is useful to us. I'll show you here in a second. Here's an example of two isotopes. Here's your plain old hydrogen atom on the left-hand side called protium. You know, because hydrogen atoms are usually called, you know, if we're dealing with the hydrogen atom, if we're just dealing with the proton, it's called an ion. We call it a proton. You know, we refer to a hydrogen atom as a proton anyway, because the electron. No, just take my word for it. So we call it protium. One proton, one electron. Here we see next to it deuterium. Deuterium has one proton, one electron, because that's still hydrogen, but it has a neutron. Even though it has a neutron, it's still hydrogen, but it's called deuterium. It's unstable. It wants to get rid of that neutron. Next to it is tritium. Tritium has two neutrons, one proton, one electron. It is still hydrogen, but it is still unstable. It's more unstable than the deuterium is because it has those two neutrons it's trying to get rid of. Deuterium can be combined, however, with oxygen to form what we call heavy water. Heavy water is used in nuclear power plants. It's used to help absorb other neutrons. So deuterium has a use. So does tritium has a use. But the tritium and deuterium are radioactive isotopes of hydrogen. They are unstable. They will release energy to try and kick out those neutrons. And so this instability makes the instability of the nucleus makes the atom radioactive. It will give off gamma rays. It will give off beta particles and alpha particles over a period of time until we get rid of those extra neutrons. What are they good for and why do we care in healthcare in A&P? Because radioisotopes can be used for treating diseases, for detecting pathological conditions. For example, we see here a picture of an X-ray of a thyroid. Now, the thyroid gland located in our neck, right about the collar level, if you will. If you want to know where your thyroid is, if you feel the front of your throat, there's a little dimple that you can feel, and that little dimple is where there's a slight gap in the cartilage that makes up our airway, and our thyroid is right below that dimple and comes up on either side. There's two lobules. You can see it on the illustration here. The dimple would be right in this dark spot, and then we have these lobules here. The thyroid is a gland that controls all of our metabolic activity. How rapidly do we burn up glucose? How rapidly do we burn up carbohydrates, sugars? You know, it tells our cells to actively process sugar to get energy. So it controls all the chemical reactions in our bodies, or at least most of them anyway, at least the ones dealing with energy. But it releases a substance known as thyroid hormone. Now, for thyroid hormone to be made, we need iodine. We need iodine in our diet. Iodine, when combined with a substance inside the thyroid gland, forms thyroid hormone. If you were to give a patient a very small amount of radioactive iodine, iodine in the human body only works in one place. It all ends up in the thyroid gland. Radioactive iodine will show up on an X-ray. And this scan of the thyroid gland shows you where it's being taken up. Everywhere that's glowing white is where the iodine is being incorporated. Where there's a dark spot tells you there's a region there of the thyroid gland not working. So with a simple use of a radioactive isotope of iodine with a half-life of about 12 hours, so it's totally gone out of your body in about 48 hours, we can detect the presence of a tumor. We can detect the presence of a nodule in the thyroid that's not working properly. We can detect an area of the thyroid gland that's working overtime, if you will. We can observe all this by using the radioisotope. We can also use a radioactive isotope of iodine with a longer half-life to treat a cancer growing in the thyroid. The thyroid's is the only place that radioactive iodine will go. And if we have a cancer cells growing in the thyroid, we can destroy the cancer with the radioactive iodine without surgery. So now, of course, most most treatments are using radiation to kill cancer cells now uses proton beams and structures like that. So we probably don't use isotopes as much as we did for cancer treatment, but it is still very effective in determining the uptake, the activity of certain organs and glands. And this is a good example of one right here. Okay, now moving on. So we see atoms. Elements are made of atoms. Atoms are made of subatomic particles. The subatomic particles are protons, neutrons, and electrons. Electrons and protons are always balanced. They're always the same. Neutrons can be variable. And if we have a different number of neutrons than what we would expect, we have an isotope. If the atomic mass number is different from the norm, then we have an isotope. And isotopes are radioactive. Now let's take a look at what happens if we take atoms and combine them together. Molecules get formed. A molecule is a combination of two or more atoms. Water is a molecule, H2O, 2 hydrogens and 1 oxygen. Atmospheric oxygen is O2. You've probably heard that term before if you've been involved in any kind of healthcare, or if you just heard it, O2, the breathable oxygen, 2 oxygen atoms. We don't breathe the elemental oxygen, which is just 1 atom. We breathe what we call atmospheric oxygen, which is 2 oxygen atoms. Nitrogen has 3. A nitrogen molecule has 3 nitrogen atoms. Molecules, 2 or more atoms linked together. Compounds, it says, well, that's 2 or more different types of atoms, but we generally refer to everything as a molecule. Like glucose, the formula for glucose, C6H12O6, 6 carbons, 12 hydrogens, and 6 oxygens. That's sugar. That's a simple sugar. We say a molecule of glucose, or a molecule of water, or a molecule of atmospheric air. So that's how we describe it. We don't say a compound of glucose. No, we just say a molecule. But they're made up of atoms linked together, joined together. Molecules are made up of atoms that are chemically joined together, not just mixed, but chemically joined together. Mixtures are different. Mixtures are very simple. Mixtures are just the physical intermixing of different substances, 2 or more components. For example, if you are making iced tea, sweet tea, You mix together water and sugar, and of course the tea bags. And now you have sugar in the tea. You have the tea itself, that has come out of the leaves in the water. And you could physically separate the sugar from the tea. You could easily take a filter and filter out the sugar, because the sugar has not been altered other than the fact that it's floating around in the water, in the tea. The sugar hasn't been changed when it goes into tea. You could make salt water. You could add sodium chloride, table salt to water, and you could filter out the water, or you could filter out the tea. The salt, because there's been no chemical change to the salt or the water. Mixtures are where we physically intermix substances together, but there is no chemical change to the substance. Adding sugar to tea, adding salt water, adding salt to water to cook with, there's no physical change to either one. The water doesn't change, the salt doesn't change. The water doesn't change, the sugar doesn't change. When you, I'll get back to that in a second. So 3 types of mixtures: solutions, colloids, or suspensions. A solution is a liquid that's transparent. It's usually based off of water. A solution depends on two parts: a solvent, which is the dissolving medium, meaning if you take a tablespoon of salt and put it into a glass of water, the salt disappears when it goes in the water. The water is the solvent in this case. The glass of water, let's be more precise, a beaker containing a liter of water, that's more scientific sounding. A beaker that contains a liter of water, and you add 100 grams of salt to it. The water is the solvent. The water is the dissolving medium. The solute is what's getting dissolved. It's what goes into solution, as we say. So if you dump 100 grams of sodium chloride, table salt, into a beaker containing 1 liter of water, the salt will go into solution. It will dissolve. The salt is called the solute. The solute's what's getting dissolved. The solvent is what's dissolving it. Solvent is usually water. The solute can be sugar, it can be salt, it can be anything. In our blood, we measure blood sugar. Glucose is the sugar that we measure when we measure blood sugar. Glucose is the simplest form of sugar as far as our bodies are concerned. It's also the primary source of fuel for our bodies. So we measure blood sugar when you get blood workup done. It tells you, what's your glucose level, and it gives you a number. Okay, and we use that number as a reference point. Are you too high or too low? A patient that has diabetes often refers to their diabetes as sugar diabetes. That's an old term, but many people still call it that. And if your patient has diabetes, they are always focused on measuring their blood sugar levels, which we also refer to as blood glucose levels. Glucose is the solute. It's being dissolved in the plasma of our blood. Plasma is the water component. Blood is 55% plasma. Plasma is nothing but salt water with some proteins thrown in there. It also is how we carry the sugar around. So we dissolve sugar in our blood. Plasma is the solvent. Sugar is the solute. Solutions are transparent. You can see through them. You have a bottle of Coke and you pour the Coke into a glass, you can see through it, even though it's dark, even though the caramel coloring in there makes the Coke dark brown. You can still see through it from one side to the other. It's not cloudy. If your Coke is cloudy, there's something wrong. So it is transparent. A glass of iced tea is transparent. Coffee is actually transparent. Even though it's dark, you can still see through it. When you're pouring it, you can see through it. It is the water in the coffee is the solvent, and the coffee grinds that you're brewing the coffee from is the solute. And with any good solution, you could filter everything out because there's no physical intermixing. There's no change to the water. The coffee is mixed with the water, but if you ran it through a small enough filter, you could filter out the coffee. You could filter out sugar from tea, and you would have, you would separate the sugar from the water or salt from water because there's no change to it. So solutions are, like any good mixture, you can separate out the components. You could, doesn't matter what even if you have these little flavor packets that you put into a bottle of water, to give it orange or yellow, orange or lemon or whatever fruit flavor you like, doesn't matter. Given a small enough filter, you could filter out all the parts of that till you had nothing left but plain water behind. Solutions are always transparent. They're always, because you can always see right through them. Now, how do we measure solutions? Well, the simplest way is to measure their concentration in percent. If I take my beaker with a liter of water in it, and I dump, which is 1,000 milliliters, and I dump 100 grams of salt, sodium chloride, into that beaker. Well, 100 grams of salt, 100 is 10% of 1,000. So I have just made a 10% salt solution, 10% sodium chloride, 100 grams of sodium chloride in 1,000 milliliters of water, 10% salt solution. What if I had 400 grams of glucose into a liter of water? 400 grams of glucose into 1,000 milliliters gives me a 40% glucose solution. Very, very simple, very easy way to measure solutions. And this is how we do most of our solution measuring in healthcare. IV bags hanging on a patient are usually expressed as percents, like normal saline, 0.9% sodium chloride, a 5% dextrose solution going into your patient has a 5% sugar concentration. It's simple. It's easy to understand. We know what it means. That's one way to measure solutions. A little more precise way, we measure like blood sugar levels. And we use milligrams per deciliter. A deciliter is 1/100th of a liter. And so we measure the amount of glucose in a deciliter of blood when we do blood workup. And so we say milligrams per deciliter. Somewhere between 80 and 100 milligrams per deciliter is a normal blood sugar level. Usually we say, what's your blood sugar? It was around 90. Your patient, the blood sugar was 90 or 80 or 100 or 150 or 3,000 or whatever. Not 3,000, but it's possible. It'd probably be oozing sugar at that point. But the point is that we use milligrams per deciliter. Now I will say that's an awkward way of saying it. What was your patient's blood sugar? Well, it was 110 milligrams per deciliter. Mostly when you're asked blood sugar levels, you're going to give the number. It's understood that it's milligrams per deciliter. So these are two good ways of measuring concentrations of solutions. the one that's used the most frequently is percentage. Now, there is a third mechanism that we measure by, and you're going to have to wait until Monday to hear that, because that's called molarity, and I can't describe that in the time left. So anyway, let me get us out of here. Does anybody have any questions about anything before I get us out? Okay. In that case, I will pull the plug, and I will see you all next week. So have a good day.